Welcome back to the last session of today's EasySpin Academy 2020. This is not a topical session. I'm just going to go over some of the questions that appeared on Slido over the last 5 sessions or 6 sessions. Before that, though, I'd like to remind you of a few things. First of all, I want to mention again the t-shirt campaign that we're having. In fact, I think already 15 t-shirts are committed. We are not making any profit of this. Any profit from these shirt sales go to a foundation. So if you want a t-shirt from this academy, go to bonfire.com, and I think the link has been posted in Slido to get one. The second thing I would like to show is the happy hour space we're going to have starting in half an hour. And the link is on the Academy website, and you should have also received it in your email. Here we are. So I just logged in. I had to give myself a name, which I already did ahead of time. Basically, this is a large space where you can see where you can see yourself in the center, and you can use your cursor keys to walk around. And so, and then here in the center, you will see indications of where to go. So this is basically a series of rooms. There's a central plaza here. And at the bottom, you can look at the mini map of the space. This is a central plaza, and there's several white doors. The ones on the left go to the so-called easy bar, and the doors on the right go to the spin bar. And then there's gateways on the top and on the bottom, which lead to the north and the south beach, and to a bonfire and to the dock. And then in addition, we have a pepper bar and a salt bar here. And we have breakout rooms for like smaller rooms that are up here. There's 5 of them. And there's another 5 rooms that are down here. The rooms here on top are numbered by spin quantum numbers. So room 1/2, room 3/2, room 5/2, and so on. And the ones here at the bottom are have some topic names like nitroxides and pulse CPR. So when you join, just go in and wander around using this mini map. You can modify your avatar again here at the bottom by click on change character, and you can change your shirt and what character you want to look like. And as you walk, and so I'm going to go over to the easy bar. As you walk, you will see people, and whoever is in your range will show up with a video. Voila, and here we are in the easy bar, and you can see, if people are seated on any of these tables, you will be able to talk to the other people. These dots are, whenever you see these dots, these are so-called private spaces, which means you can have a conversation just with the people who are sitting at this table, and nobody else can hear you. If you're not in a private space, everybody within a certain radius will be able to hear you and see you. And you can change the radius of your personal space by clicking here at the bottom. It says interaction distance. And if you just keep clicking, it goes from small, medium, a little larger, and full. And feel free to explore all the areas. On the right-hand side here, you can see a list of participants. Right now it's just me because the area is still password protected. And but you can then find somebody by clicking on that person's name, and it will give you an option to show you an arrow how to get to that person. What else is there? These are kind of, I think these are kind of the key points. And I guess we'll see all of you later in this space in about 25 minutes. Well, it's right now password protected, so we'll open it up as soon as this Q&A session is over. So here you can see the topic rooms. Here's a room on MATLAB. So if people are interested in MATLAB, they might just go there and meet. This is more of a conference room, and there's also some whiteboards. If you have a tablet or writing capabilities on your computer with a mouse, you can just stand in front of this whiteboard, and you press X. Then you can access the shared whiteboard, and you can actually then you can draw on it. So there's a few of these interactive tools around, and you can just walk around and explore them. Going back to the main area here. Some of the areas are blocked off. You can for example see that right now here there's a bunch of plants in front that don't let us through to get to the dock. Depending on how many people there are, we'll open these extra rooms to make sure there's a sufficient but not too high density of people in all of those rooms. All right, so that was a quick introduction to Gather. Just wanted to share it with you so you have a basic familiarity if you haven't used that before. All right. The last thing before I get to the questions is how to update EasySpin. Well, you can always check the website and download the latest version. But once you have a version installed, you can just from the command line in MATLAB check whether you need to update. And you just type EasySpin update and then press enter. And this will actually pull the EasySpin web server and ask if there is a more recent version. In my case, I'm using the most recent version, so there is no update available. So that's something that should work for you and should make it easy to update. So we've got a couple of questions. One that I found interesting and important to talk about is about different line broadening models. When to combine them, when you can combine them. So as you've seen, we have this sys.lwpp, which gives you some convolutional broadening, right? And then we have sys.hstrain, for example, or A-strain or G-strain. And these are all strain broadenings. Let's write them out. G-strain is for the G tensor. A-strain is for the hyperfine tensors. And H-strain, which stands basically for Hamiltonian. H stands for Hamiltonian. It means just the energy level. The energy levels are scattered. Whatever it's G or A tensor, doesn't matter. Just a very generic distribution of energy levels. And H strain and G and A strain and LWPP can produce very, very similar effects, right? So I discourage you from using them at the same time. You really have to think about, first question to answer when you do model broadening is, A, do you want to think about the physics behind or not, right? And so if you don't want to care about that, and you're just really just interested in the line shape positions and you don't want to have perfect fits, then use the convolutional broadening. And that is often a very good starting point. Now, you might not be able to fit your spectrum really well with that because broadening always has a physical origin. In that case, you have to move on to the next level of line broadening modeling. And you have to basically choose which of these strains to use. Okay, so that will depend on your system, and I would suggest to consult the literature on that. The simplest way to go about is to first use H-strain. Else, the LWPP is an isotropic broadening, right? So it applies in a powder spectrum, it applies to the same whether it's the X, the Y, or Z direction, and it's in millitesla. Whereas the H-strain can be isotropic or anisotropic. And it's in megahertz. Let's quickly see how these two can produce the same effect. So first, let's define a spin system with a G tensor, 2, 2.1, 2.2, and let's add some line broadening. Okay, that's a line broadening of 1 millitesla. Okay, then we specify microwave frequency 9.5, and we'll simulate the spectrum. Okay, so actually let's specify the range manually. Now that we have the first simulation, it's probably from 300 to 350 is a good range. Run this again. Yep, that looks good. Okay, now we're gonna take the same system, run it again. We'll call it sys1, but we're not gonna use LWPP, we're gonna use H-strain. But now we have to convert it to megahertz, and 1 millitesla is about 30 megahertz. And we're gonna now simulate both spectra. Now I have to run this twice and ask EasySpin to return the spectra. And finally plot both of them. Control Enter. Right, and you can see there's perfect overlap between blue and red. I can change the H-strain a little bit larger to make it larger. As you can see there, they don't quite They don't, this one, sorry. They don't quite agree. There you go, okay? So I just made a small mismatch. They don't quite agree. Now, if this works for you, if this matches your experimental spectrum, you can use LWPP or Hstrain, isotropic Hstrain. Makes no difference. But as soon as you have an anisotropic situation, where different parts of the spectrum are broadened differently, like 35, 50, 100, then like this here, look at the red spectrum. Low field is much more broadened than a high field edge. Then you do need to use Hstrain. Hstrain is basically the lowest level of modeling for an anisotropic broadening. It's generic. It's not convolutional, but it's generic. Does not make specific assumptions about the broadening mechanisms. So I would say level 0 of modeling is LWPP. Then level 1 is Hstrain, which allows you to go anisotropic. And then level 2 are the tensor strains. Right? You need G strain, A strain, and D strain. Okay. And never mix broadenings from these different levels. That is kind of the bottom line of this line broadening. Okay. I think that was an important question. There was also any questions about isotopes. Okay, how much they slow down a simulation. For example, let's take a copper simulation, right? A copper simulation which has some G values of 2 and 2.2, very crudely, and the nuclei. Let's take just copper. And let's take a hyperfine coupling of 20 and like 400. And simulate the spectrum. You probably have to drop the low frequency edge a little bit to accommodate the full spectrum. And we probably should add a little bit of line broadening as well. Start out with 1 millitesla. Okay, I think this is a little too low, the edge. All right, so here you see a typical copper spectrum. It has the Z direction, it has resolved hyperfine with 4 lines, because both copper nuclei are spin 3/2, so they have 4 hyperfine lines. You can see that there is structure to them, right? And the reason is that the outer one is from copper 65 and the inner one is from copper 63. So these are basically 4 quartets that are almost the same splitting, but not quite. And the reason for the difference is that they have different gyromagnetic ratios. So if they sit in the same position in a molecule, they just respond differently, or they couple differently to the electron spin. And how does EasySpin handle that? Well, first it looks up, what are the copper isotopes? It finds there are 2 of them, and then it runs one simulation for each of them. So in the case of this simulation, the simulation time goes up a factor of 2 because you have 2 isotopal logs. If you just specify copper 65, then simulation is twice as fast, and you only see just a 1 clean 4-point hyperfine splitting. Right? If you have titanium, let's take the case of a titanium here. The hyperfine, the G and hyperfine values don't match, but for titanium things get a little more complicated. Because in addition, you can see there's now multiple things going on. We fire up isotopes, and you look at titanium, you can see there is titanium 47 with 7% abundance with a spin of 5/2, and titanium 49 with a spin of 7/2 with a 5% abundance. And all the remainder of the titanium isotopes are non-magnetic, so those lead to the sharp central line where the molecule only has the unpaired electron and nothing else magnetic that's relevant. And then the other peaks are from these other isotopes that are present in the magnetic isotopes of titanium. So I hope that answers that question. Okay, Bader Bruin asked about if relative intensities between a spin 1 and a spin 1/2 system are comparable. I think they are, because we're using the same theory for everything. So the transition matrix elements that calculate those intensities should make those spectra perfectly comparable. So at least theoretically they are. And I don't think anybody has reported to us an actual comparison of a triplet with a radical signal where they did spin quantitation. It would be great to hear about that and how well EasySpin represents the relative intensities. So what else? Yeah, somebody was asking about how to simulate Lanthanides. I think it was Lei Sun. Where neither the spin nor the orbital angular momentum are well defined. And you can actually squeeze these types of simulations into an EasySpin jacket. And the way to do that is basically to use the S field for your total angular momentum quantum number like J, and then use very generic Hamiltonian terms. Instead of a G tensor or an A tensor, you can use higher order operators. And I'm going to show this here in the spin system section. If you scroll down, there is a section on orbital angular momentum and spin orbit interaction, but there's another one about higher order operators. So what you can do, you can specify so-called extended Stevens operators that allow you to build any Hamiltonian you want that still kind of fits in the angular momentum picture. Doesn't have to be spin or orbital, it can be just some generic angular momentum. These extended Stevens operators are quite some beasts. I'm clicking over here to the reference, and they're given here. But this way, you can build basically any Hamiltonian that is based on angular momentum. So answer is yes, you can simulate Lanthanides with EasySpin. What other let's look for another question. One question was when to use which level of theory. We've seen that both for garlic and pepper, you can choose which theory level you want. And there's always the exact level that makes a minimal number of assumptions. And then there is some sort of approximative treatment that is much faster and takes less memory. So I would recommend always use the exact. And then go back to like a more approximate treatment only in special circumstances. And one of them, of course, is if you want to understand how your spectrum comes about. Often we think in a very first order perturbation theory picture, that the splitting is, hyperfine coupling and hyperfine splitting are the same and so on. And if you do a perturbation calculation, then you can see how that differs from the exact treatment, and that allows you to kind of learn a little bit more about the physics. So that's one reason you would go to a lower level of treatment. And the second is if your spin system is really large, it has an electron spin and maybe 5 or 10 nuclei, then the exact treatment gets very taxing on your computer. You need a lot of memory and a lot of time. But very often out of these 5 or 10 nuclei, only very few of them are strongly coupled. Only a few have large hyperfine couplings. So what you can do, you can keep the exact treatment for those nuclei, and then you can use perturbation treatment for the other more weakly coupled nuclei. And this is often a reasonable approximation. If you have this situation, of course, it's hard to test because you're going to reduce the theory level only if you need. The way to test it is to do a single crystal simulation, right? A powder simulation takes like 100 times longer than a single crystal simulation. Do a single crystal simulation with the exact level and with the perturbation level and see if they match or if they're close enough. And if they're close enough, you can then do a powder simulation at the perturbation level. So that's one way to go about it. A second strategy is to just drop 1 or 2 nuclei and to reduce the system size a bit and then see whether the exact method and the perturbation method are kind of consistent. And as long as you just add nuclei with small hyperfine couplings, you won't mess with that relationship between exact and approximate theory. And this way you can just be sure that you're not screwing it up. So that was another question. I'm going to go switch over to the Slido right now and see what are the most popular questions and briefly react that. Okay, and thank you, of course. There was a question whether these sessions will be available on YouTube, and the answer is yes, so you can rewatch. We know that some of this might be fast for some of you, especially if you're not familiar with that particular area of sub area of EPR. But we wanted to have something for everybody in this in this workshop, in this academy. But you can always come back and watch the streams later. Happy hour password. There is no happy hour password. It's password protected now, but we're going to open it in a few minutes, I think in 10 minutes. And then everybody can just join with the URL that's provided. I think we talked about the line width strain. We talked about this here. Sonia is asking about global fitting multiple spectra. I will talk about fitting tomorrow. I'm not entirely sure we're going to get to global fitting much, but what you can do with chili, you can also do with pepper. So there is no difference. So what else is there? While specifying the G-tensor in EasySpin simulation, is it always in the order G, X, Y, Z? Or do the order in reverse also work? If specify the hyperflow tensor also in the same order. So yeah, what about the order of the values? Maybe that's an important thing to talk about. The important thing is to always consider there is a molecular reference frame, right? And G is on A and all the tensors are defined relative to that. So if you say sys.g equals, let's say 2, 3, and 4, then the first one, these corresponds, these give the tensor x, y, and z directions. Okay. If you have no tilt between the tensor and the molecular reference frame, then the tensor x aligns with the molecular x from the molecular reference frame, which is also, we can call this like xm, ym, and zm for the molecular axes. And the tensor g's, let's call them xg, yg, and zg. Right. If you don't specify a tilt, the xg aligns with the xm, and the yg with the ym, and the zg with the zm. Right? If you specify a tilt, sys.g frame, right, you could specify now 0, pi over 2, 0, then that will turn the tensor based on these Euler angle prescription. And then you will, the angles or the axis will not align anymore. But if you don't specify this, all the tensors are initially aligned with the molecular reference frame, which is fixed to the molecule. And again, maybe go back to the documentation here and show that this is a very important page here about coordinate frames that defines how these frames are defined. Right? There's the molecular frame, and that's just a reference frame that's fixed in a molecular paramagnetic center. Right. And this molecular frame is of importance, for example, if you're doing quantum chemical calculations with ORCA. ORCA does the calculation within some sort of frame that derives maybe from the crystal structure, right? So that the XYZ axis from the crystal structure, they will make the molecular reference frame. And there's a function in EasySpin that allows you to import ORCA results directly into a spin system for EPR simulations, if you've calculated EPR properties. And this import function will use the ORCA kind of simulation frame as the molecular reference frame, and all the tensors are oriented relative to that. Okay, I hope that clears that up. There is some people upvoted questions about where they can download the folder and script files. That is on the EasySpin Academy website, easyspin.org/academy. One of these bullet points, you can find it here, yeah, is a zip file containing all demos and exercises. You can download it here. And at the end of the workshop, we'll provide a new zip file that contains all the solutions to the exercises. We've written them out already, but we're probably going to do them with some minor adjustments based on the experience from these workshops. So at the end of the workshop, you'll get a file with everything that will allow you to retrace what we did in the workshop. Let's see if there's any other questions. There is some questions, requesting specific topics. We're gonna do the specific topics on the third day, on Thursday. So those sessions, we still haven't planned them out. Depends a little bit on your feedback. And we are planning to hold a poll about which topics to cover tomorrow morning. So we'll be able to collect some input from you guys separately on what to cover. Okay, so watch out for a poll tomorrow, and please participate in the poll if you want your topic to get covered. I can't promise we'll be able to do it because there's only limited time and there's so many different things. EPR is such a rich field that it's been a challenge for EasySpin to keep everything organized together so that everybody can simulate their spectra from the lanthanides up to the organic radicals across the periodic table. Okay, let's see if there's anything else. There was one question by Hugo about how many nuclei one can maximally include in a spin system. In principle, there is no limit. It really depends on your computer resources. If you have, adding nucleus, if you add a proton, it will increase the spin system Hilbert space by a factor of 2. Right? And so if you add 10 protons, it will increase the spin space by a factor of 2 to the 10, so it was 1,000. So the memory requirements to setting up the matrices get larger and larger, right? So you need many gigabytes of memory for large spin systems. But EasySpin has no hardwired limits. You can have as many electrons and as many nuclei in your spin system as you want. Okay. What else is there? There's one question from Tanya that just came in. Maybe that's the last one we'll take here before we head over. The principal direction corresponds to the rotation of the molecular frame. Actually, let's go back and actually look at this example right away. So let's take a G-frame rotation of 30, 50, and 10, convert that to radians, and now fire up the new function rotview sys.gframe. We can actually feed it already a set of Euler angles, and we'll use those to construct the plot. So here is the plot. Okay, so what you can see here, you can select here that this relates to a G-frame, and if you click here, it will label the axis correspondingly. So you can see this, the molecular frame with the M here, XM, YM, ZM, in dashed lines. And then the tensor frame is labeled XG, YG, and ZG, and also indicated with this tensor ellipsoid or tensor potato. So basically what the Euler angles give is the rotation you have to do to take the molecular frame to align with the tensor frame. While the tensor is fixed in the molecule, I'm not going to rotate the tensor. We're just going to look at the frames. So you take the molecular XYZ frame, and then figure out what Euler angles you need to rotate that molecular frame to match the tensor frame. That's what these angles mean. Okay, I think that is probably enough for today. And we're just 1 or 2 minutes away from the happy hour, so I won't hold you up. Please join us over at GatherTown and let's hang out. Make sure you be aware that your video will be on, but you only will be visible to people who are standing close to you. Okay? So thank you for participating on day 1. We'll start day 2 at the same time tomorrow, so 7:30 Seattle time, and I hope to see you all there for lots of talking about least squares fitting. See you in happy hour.